Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to the second lecture of the series. So in the previous lecture I had given you a brief introduction of what we are going to or the kind of problems that we are going to deal with in this course, and even before we move on to the methods that we are going to use to understand and deal with these problems, what we are going to do next is to actually elaborate on at least two problems, most commonly existing problems in microdata, namely omitted variables and measurement error problems. That is what we are going to do next, and then we would move on to methods that can be used to deal with these problems. So, typically in a regression model, so consider this model over here, y as a function of d. So, let us say that d is our variable of interest. So, typically in this sort of a model, what we are interested in is this parameter on d beta, which essentially tells us how d affects y, and this x over here are basically other exogenous covariates that go into the model. So, as the first point over here says, we are interested in the effect of d on y, and we believe that x affects both y and the selection into treatment. So, there can be two, so x essentially represents two types of issues. One is the selection on observable. So, if we observe x and that is how d is selected, then controlling for x takes care of the problem, and the other is particularly in the case of experiments, as we would see later, sometimes we would run an experiment conditioning on variables such as x, and those are called conditional randomization. So, x also serves that purpose. Now, the typical mean independence assumptions that we require to have a consistent or unbiased estimate of beta is that expectation of y naught given dx is equal to the expectation of y naught given x. What does this mean? This just means that the initial value of y, which is y naught, let us say d is some kind of an experimental intervention. So, even before the intervention has happened, then the initial value of the outcome variable that we observe, that should be independent of this intervention, in the sense that suppose we think of an experiment as a group of people where some people are getting the intervention, who we call the treatment group, and some people are not getting the intervention, who we call the control group. In that case, what you take is the value or that you are trying to affect through this intervention, let us say health outcomes or education outcomes, and initial education outcome or initial health outcome even before the experiment or the intervention takes place is essentially represented by y naught. And what we are saying over here is that the assignment of treatment given by d is independent of this y naught once you condition on x. So, conditional on x, d is independent of y naught. This is what the condition says, and that is what the mean independence condition is, specifically in the case where we have conditioning variables represented by x. The other point is that of homogeneous treatment effect, that is expectation of y1 given x is equal to expectation of y naught given x plus beta, which means that this effect due to the intervention is same for all individuals in the sample. In this case, of course, if you have such conditions, these conditions are met, in that case OLS will recover the treatment effect. But the problem comes when these conditions are not met. So, let us take a specific example to understand this. So, suppose we take the example of returns to education, and let us say D is an indicator of whether a person has a master's degree or not, and we want to understand whether a master's degree actually leads to higher earnings potential for the individual, higher wages, higher earnings, higher income, and so on. And let us say X is represented by so X represents secondary school test scores. So what this means is that if graduation is more likely for those with higher secondary school test scores, but random within test scores, then the OLS of Y, so this regression equation that we saw before, will uncover the causal effect of D on Y, which is basically the causal effect of graduation on earnings. However, if graduation also depends on the secondary school attended, so what we are saying over here is that this is selection on observables, because here we observe the value of X, which is secondary school test score, on which based on which D is determined. But suppose there is another variable which is the secondary school, the type of secondary school that is attended prior to college, and that also affects income, then the selection problem will remain even after controlling for secondary school test scores. So what this means is that in this case secondary school attended would be a sort of an omitted variable which you do not observe. So let us say a person was going to a public school or a private school, in addition to the test score that you get from your secondary school, after your secondary school, the type of school that you go to also affects your earnings potential later in life. In that case, if you do not observe this type of secondary school, then you are not able to control for this in the regression equation that you saw over here. And when you are not able to control for an important variable, it gets loaded into this error term over here, and that creates a problem. This is the typical case what we call the omitted variable situation, and what we are going to do is to understand the omitted variable bias. So in general, the analyst may be groping for good measures of what should be in X, and we are never fully able to capture all the variables conditional on which D is random. So what this means is that all the omitted, so we can so in the previous example you saw that we have one omitted variable, one potential omitted variable, which is the secondary school test scores, and we are able to control for it. But then there is another omitted variable which is the secondary school type, and we are not able to control for it. So in general, in any regression or any question that you ask, a causal question, you can never be fully sure that you have accounted for all the variables that are likely to be, or that have the potential to be omitted variables and potential to generate an omitted variable bias. Now because you cannot be sure that you have accounted for everything under the sun, there is always a problem with omitted variable bias in most microeconomic estimations, and hence we need methods to solve that problem. But as I said, even before we go to the methods, let us first understand how what the omitted variable bias is. Suppose we are interested in the returns to schooling and Y represents earnings. So this is the true relationship between earnings and schooling, which is given by X, let us say. Okay. But we also have another variable, typically ability, which affects the earnings potential of an individual and also affects X, which is the schooling outcomes of an individual. So for what we mean by that is a child who is more able or maybe more intelligent or has higher motivation is not only likely to attain higher levels of schooling and do better, perform better in schools, but they are also likely to have, because they are more able, they are also likely to have higher wages or higher earnings, right. So A over here affects not only X but also Y. So the relationship between X and A can also be written as A equal to eta plus delta X plus U, let us say. So what this means is that we have another equation which gives you the relationship between X and A, and in the first equation what we saw was the relationship between A and Y. Now what we have is, if we estimate the so generally what happens is so now we get to the problem of omitted variable bias. So typically what happens is we do not observe ability, let us say, and this is analogous to the problem that we discussed in the previous slide, where we were saying that we have the secondary school type and we do not observe the secondary school type, and this is the exact problem that we have over here. We typically do not observe ability of individuals. So what do we end up estimating is the following equation. We typically end up estimating y beta x, which is schooling, plus the error term, and we do not observe ability. So what we are asking over here is that if we miss out on ability in this regression, or if we omit ability in this regression, then what is the problem in the estimation of beta? So this is the observed equation or the observed relationship. Okay. So the OLS estimate of beta given by beta OLS, beta hat OLS, is nothing but x prime x inverse x prime y from the reduced equation or from the observed equation. However, the true relationship of y, remember, comes from equation 1 over here. So we can write this as x prime x whole inverse x prime right. Now just for simplicity, for the time being, we are going to consider a mean difference model, so that we are not so much bothered about the constant, and the constant is taken out in the mean difference model. So suppose we take y minus y bar and x minus x bar, so so the constant is included in the model, and then we are left with this. Then what we can write is the following. So what we have are three terms over here. The first one is x prime x whole inverse x prime beta is three terms. We have x prime x whole inverse x prime x beta. The second term, which is x prime x whole inverse x prime with gamma a, so x prime a times gamma, and the third term where we have x prime x whole inverse x prime epsilon. But remember, in the true model, of course, the relationship, the mean independence assumption holds, and hence the covariance between x and epsilon is 0 in the true model, and that is why we have a 0 over here. The expected value of epsilon given x is equal to 0. So what we are left with then is essentially beta plus this term, sorry, this would have an expectation in the beginning. So what we have is expectation of x prime x whole inverse x prime a gamma. Okay. Now let us see what this term means. Okay. So what we have now is, let us get back to the previous relationship that we outlined between a and x. From there, what we know is that the OLS estimate of delta, which is delta hat OLS, is nothing but x prime x whole inverse x prime a, right, and that is essentially what we have over here now. Right. So what we can write is, this is equal to beta plus delta gamma. Right. So what we are saying is that the expected value of beta hat OLS is equal to the true value of beta plus this term delta gamma. which is coming from the fact that there is a relationship between the omitted variable ability and y, and there is also a relationship between the omitted variable ability and x. If any of these terms is equal to 0, we do not have a bias, but given that both, if in the case that both of these terms are non-zero, then we have a bias which is equal to delta gamma. So, this is called the omitted variable bias. To understand the omitted variable bias in practice, let us consider this paper by Grilich's 1977, where he tries to estimate the returns to education. So, what Grilich's does is he discusses the estimation of returns to education using data from the US National Longitudinal Survey, and the equation that he estimates is essentially what we just saw, log y, which is the log of earnings, as a function of schooling, which is given by S. And what he finds in the OLS estimation of this equation, where there is an omitted variable obviously that we discussed, which is given by ability, he finds that the coefficient on S is 0.068. Now, we just saw that in the absence, or when you do not observe a relevant variable, which we typically call the omitted variable, then this coefficient estimate of beta is likely to be biased. So, what he next does is to elaborate this point. He, in this particular data set that Grilich's uses, there is a variable that can be used as a proxy for ability, which is given by the IQ test scores. So, what you have is that NLS data contains IQ test score, which Grilich's then includes in the previous short equation, and now what you have is the true equation, which is log earnings as a function of both schooling and IQ. Now, remember in the omitted variable bias, what we are saying is that when IQ is omitted in the previous equation, then IQ is likely to be, because IQ is likely to be related to both S and Y, it creates a bias in the estimate of beta, which is 0.068. And this is exactly what we observe over here. So, when IQ is indeed included in the regression equation, what you see is that the coefficient of beta falls from 0.68 to 0.059, and the coefficient on IQ, which we had defined as gamma, is 0.028. Now, because this coefficient has gone down, which means that what we had was an upward bias. So, recall that what we had written or what we derived was this expectation of beta OLS is equal to the true value of beta plus the omitted variable bias given by delta gamma, right. And what we observe is that this expected value of beta OLS is 0.068 is greater than the true value, which means that this value over here delta gamma must have been greater than 0, and what you observe is that gamma is greater than 0, which is given by 0.0028, which means that delta must also be greater than 0 in this case. Okay. And this just shows you numerically what we derived in theory as the omitted variable bias, how that plays out in the data. What we do next, so this is basically about omitted variable bias. What we would do next is the measurement error problem. So, this was one problem, and the next problem is the measurement error problem. So, typically what happens is, sometimes in economic applications we cannot collect data on the variable that truly affects economic behavior. So, measurement error is reporting error in the actual variable under consideration. Measurement error does not concern a proxy. So, for instance, reported income as opposed to actual income would be a case of measurement error, whereas asset is a proxy for income. Okay. So, this is just roughly some approximate examples to understand the difference between proxy and measurement error, but typically it is very difficult to distinguish between the two. So, what we are going to do is we are going to consider specifically two cases. One is where the measurement error is in the dependent variable, which is y, and one is where the measurement error is in the explanatory variable, which is x, and try to understand how measurement error affects the estimation of beta via OLS, or in other words, does it affect the biasness or the consistency of the estimate of beta. So, let us start with the case of measurement error in y, the dependent variable. So, suppose what we have in front of us is the true relationship. So, suppose the y star reflects the true value of y. You can think of y as income, for instance, and y star is essentially true income, but often we do not observe true income. When we ask individuals about their income, it is difficult for most individuals to understand how much they have earned in the previous year by adding up all their salaries, their interest incomes, maybe rental incomes and so on. And it is even more difficult if a person is self-employed, for instance. It is very difficult to come up with one true number for income. So, often the income variable is has a lot of reporting error. So, suppose what you observe in data is the this value y, which is the observed value of the true variable capital Y, and this is the reported income. So, what we mean by measurement error is the difference between the true value and the observed value, which is suppose given by y minus y star. Okay. So, obviously, the true relationship that we want to estimate is the effect of x on y star, but what we end up estimating is the effect of x on y. Okay. Now, what we have done over here is that because we want to estimate the true relationship, we start from there and then we impute y in place of y star. Then what we are left with, if we do some manipulations, what we are left with is this addition of the measurement error to the regression error term u. Okay, so, this is essentially ends up as the observed regression, and our coefficient of interest is beta. What we want to know is that y in place of y star, whether that gives us unbiased estimate of beta or whether that biases an OLS estimate of beta. Okay. So, note that the true model in y star, when we have y star equal to alpha plus beta x plus u, that model satisfies the Gauss-Markov assumptions. Hence, the observed model will also satisfy these assumptions on u, which means that u satisfies the assumption of 0 conditional mean in both the true and the observed model, which is basically saying that the expectation of u equal to 0 and the conditional expectation of u given x is also equal to 0. And recall that this is basically the crucial assumption for OLS estimate to be unbiased. But the problem that we have now is, in addition to u, our error term also has the term which is the measurement error E naught. So, what about measurement error E naught? We want to assume that expectation of E naught is still equal to 0. So, this just means that on the average some people are reporting higher income than their actual income, some people are reporting lower incomes than their actual income. So, on the average this balances out, so that the average value of E naught is equal to 0, and even if E naught, the average value of E naught is not equal to 0, what this should do is simply affect or get loaded into the intercept term, which is given by alpha. So, we have a biased estimate of alpha in case that expectation E naught is not equal to 0, but this does not still affect, remember, beta, which is our coefficient of interest. Since we are rarely interested in the intercept, this is less serious a problem. What is of greater importance is how is E naught related to x. The reason is that the relationship between the error term and x, the conditional independence assumption, whether that is met or not. So, the usual assumption in the AMI when there is a measurement error in y is that it is independent of each of the explanatory variables. So, that the covariance of E naught given x is equal to 0 and the covariance of E naught and u is also equal to 0. So, what this means is that the measurement error is not only independent of the explanatory variable x, it is also independent of the error in y. Okay. Also, although the measurement error is in y, what we are saying is that the error part of y, which is not explained by x, also is independent of the measurement error. If these conditions are met, then beta hat, the estimate of beta, the OLS estimate of beta is unbiased. Moreover, if u and E naught are uncorrelated, which is this condition over here, then what we end up having is just a higher variance term for the error. So, now our new error term is u plus E naught. So, we have variance of u plus E naught, which is of course greater than the previous or the true standard error or the true variance of the error term. Okay. So, what this means in summation is that if measurement error is in y and it is uncorrelated with x, then the OLS estimate of beta in the observed model is unbiased. What we only have is that the standard error is higher in the case that there is a measurement error in y. However, of course, in a more complicated case where suppose the measurement error in y is correlated with your explanatory variable x, then of course the OLS estimate of beta is not going to be unbiased anymore. But what we are going to deal with today or in this particular lecture of measurement error is just to understand the classical error in variables, where we do not start by assuming that the measurement error is related to x, and we just assume that the measurement error is random, either whether it is in dependent variable or in the independent variable, and try to understand whether a random measurement error causes a bias in the estimate of beta. So, what you saw is that the ME is, if ME the measurement error in y is systematically related to one of the x's, then beta OLS is going to be, beta hat OLS is going to be biased. However, if we are considering only random measurement error, then we do not have a problem when the random measurement error is in y variable. We do not have a problem in the sense that the coefficient estimate of beta by OLS is unbiased. We might still have, of course, the coefficient estimate of alpha, which is biased. So, let us summarize what we did so far in this lecture. So, what we have done so far is essentially that we started with a discussion of problems that we typically face when estimating regression equations using OLS, and the two. So, the problems, when I say problem, what I mean is that what are the issues that lead to biased estimations of our coefficient of interest. And what I mean by coefficient of interest, just going back, is that if we are suppose interested in measuring the effect of a variable, let us say d on y, then the coefficient on d is beta, which we are interested in. And typically what we want is an unbiased or true value, we want to uncover the true value of beta. Now, what we did today is to say that there could be several problems when we try to estimate beta by OLS, and the two problems that we started with is the omitted variable bias. We saw that what you are doing is that you are taking out a variable from the regression equation, or in other words, what you are doing is that you are not able to control for a variable in the regression equation which you should have control for, because this variable is likely to affect not only y but also x. If you have such a variable, or if you theoretically can think of such a variable that affects both y and x, then the absence of such a variable, which is often the case because we do not observe all those variables and you are not able to control for all the unobserved variables. So, this is this leads to the problem of omitted variables, and this leads to the problem of omitted variable bias in the estimate of beta using OLS. The second problem that we started with is a measurement error issue. So, what we are saying over here is that suppose even the value of y and x that we are our variables of interest over here, suppose these variables are measured with error. And what kind of error? Specifically, we are talking about random error over here. So, y might be measured with some, so there is some reporting error in y, or there is some reporting error in x, And what we have done so far is to see that if there is a random reporting error in y, then that does it cause a bias in the estimation of beta. What we saw is that typically it does not create a bias in the estimation of beta through OLS when the random measurement error is not correlated with x, but it might have or it might lead to a bias in the estimation of the intercept term alpha. But typically, because we are not interested in alpha so much, but we are more interested in the relationship between d and y, which is given by beta, this is not such a serious problem. What we are going to do next is to take up the measurement error in the explanatory variable x. So far so good, and we wait till the next lecture. Thank you.